Hello, welcome to next session of practice questions of complex cases. Okay, in this session we will solve subjective questions that is not in civil services. Okay, so the first question is the state of stress at a given point in a loaded component is given by sigma x, sigma y, and tau xy. Okay, the principal stress is at the point sigma 1 and sigma 2. Okay. If the mu axis at the point are changed to x dash and y dash such that the state of stress with respect to mu axis are sigma x dash, sigma y dash, and tau y dash, tau x dash y dash. Show that sigma x plus sigma y is equal to sigma x dash plus sigma y dash is equal to sigma 1 plus sigma 2. Second, the sketch the Mohr circle for pure shear stress state and hydrostatic state of stress. Third, a cast iron bar of 30 mm diameter, 1 meter length is subjected to equal and opposite torque T applied at its end if the tensile strength of the cast iron is 80 MPa. What is the maximum value of torque T? Show the plane of failure for the applied sense of torque. Okay, so in the first question, sigma x and sigma x, sigma y and tau xy are acting. Okay, so this is the sigma x, this is the sigma y, and this is tau xy, which are acting on a system. If we draw its Mohr circle, then we'll take this plane. Okay. This is your sigma x, this is your sigma y, this is sigma x, okay. And the second stress acting on this plane is tau xy, which is anticlockwise. So draw it downward. Okay. Now next is this is sigma y. This is sigma y. Okay. The second stress acting is tau xy. Okay, tau xy. That is clockwise. So join these 2 points and find your center. This will be center. This will be radius. Draw the Mohr circle. This is the Mohr circle. So this is minimum principal stress. This is maximum principal stress. Now we can see that the distance OA will remain same and will be equal to average of sigma x and sigma y or the average of sigma 1 and sigma 2 or any of the stress acting on perpendicular planes. Summation of summation of stresses or the average of stresses acting on perpendicular plane. Okay, so now the distance OA, distance OA is the distance between the origin and the center of the circle is T. So it will remain constant. So OA is sigma x plus sigma y by 2. Okay, is equal to sigma 1 plus sigma y by 2, sigma 2 by 2. Okay, so if we can find out sigma x plus sigma y as equal to sigma 1 plus sigma 2. Okay, so this distance remains same. This distance, this distance, this distance is sigma 2 plus sigma 1 by 2 or sigma x sigma plus sigma y by 2 or any sigma x dash or sigma y dash. Okay. Now if we take any other plane, okay, then it will and the stress acting are sigma x dash plus sigma y dash. Okay, then it will also be equal to sigma x dash plus sigma y dash by 2 is equal to sigma 1 plus sigma 2 by 2. Okay, and 2 will cancel out. So sigma x dash plus sigma y dash is equal to sigma 1. Okay. So we can say sigma x dash plus sigma y dash is equal to sigma x plus sigma y is equal to sigma 1 plus sigma 2. So next is pure shear. So we have to draw the Mohr circle for pure shear and hydrostatic stress. Okay. So pure shear, in the pure shear only shear stress is acting on perpendicular planes. So this is the case of pure shear. Now we take this plane. Okay, the stress acting on this plane is anticlockwise. So it will be downward. There is no normal stress. So this is the final point. And now if we take this plane, okay, the stress acting on this plane is clockwise shear stress. So this is the final point. So this point and this point will be on the circle, and this will be a center, and draw the circle. So this is more circle. So this is the mm, uh, more circle for pure shape. Now to draw the hydrostatic state of stress. So this is the sigma. In the hydrostatic state of stress, all the stresses in all the directions are equal. This is sigma. This is also sigma. Now take this plane. Okay, draw sigma. Okay, so there is no normal stress, sorry, no shear stress, so this will be the point on the circle. Okay, so second stress is this sigma. Now again draw this sigma. This will be stress point on the circle, point on the more circle. Okay, but these two points are same, so the more circle is a point in this case. Okay, now the third question is a cast iron bar of 30 mm diameter and 1 meter length is subjected to torque T. Okay, and ultimate tensile stress or tensile strength of cast iron is 80 MPa. Okay, so you have to find out torque and show the plane of failure. Now, when the torque is acting on a body, it will cause shear stress. So, this is torque, this will be shear stress. Okay, it will cause shear stress, or we can say in positive because this stress. Okay, okay. Uh, so, if we take this element, this is the element. Okay, and draw its stresses. So, this will be the circumference direction. That x is the circumference direction, and z is your axial direction. So circumferential direction and axial direction. Okay, so this is the circumferential direction x, and this is the axial direction z. Okay, this direction. Okay, so this is, so here it will be shear stress in A, and this will be, and now this place there will be uh, complementary shear stress. Okay, so we can represent this like this. Okay. So in case of pure shear, more circle is like that, that we have drawn. Okay, and this will be the maximum principal stress plane, and this is the maximum normal stress. And as the material is cast iron, so material will fail along this plane. Okay, as the material is brittle, because brittle metal are weaker in tension. Okay, so the maximum tension is occurring at this is at 90 degree in the Mohr circle, and it will be at 45 degree in the uh, in actual. Okay, so the magnitude of this normal stress is radius of the Mohr circle, and magnitude of this is also a radius of Mohr circle, which is equal to tau. So the maximum shear, maximum normal stress will be equal to tau, and the maximum normal stress of the metal is given as 80 MPa. So sigma is equal to tau is equal to 80 MPa. So by using torsion equation that we will study later, we can find out torque putting D is equal to 30 mm and J is equal to pi by 32 big 4. Okay, we can get torque. Next, a cast iron sample when tested in compression fails along approximately 45 degrees from its axis, while when tested in torsion also fails along a 45-degree approach helical plane from its axis. Explain the reason for such failure and mention about dominating stresses causing failure. Okay, now it is uh, given that the sample of the material is cast, sample material is of cast iron. which is brittle material. Okay, so when the so the brittle material are weakest in tension, okay, and strongest in compression, and the shear stress is intermediate. Okay, so when the compression is applied on the cast iron material, so they will not fail in compression because at some plane the shear stress is acting, which is maximum, or there is maximum shear stress plane. Okay, when a uniaxial stress is applied, the maximum shear stress occur at 45 degrees to the plane of uniaxial stress. And if the uniaxial stress is compression, then it is also at 45 degree to the plane of, then the maximum shear stress will be also at the plane of compression. Okay. So when the compression is applied, so the maximum shear stress will occur at 45 degree. Okay. So the metal will fail in shear. Okay. Because there is no tension acting on the material and material is strongest in compression. Okay. Or when the torsion is applied, so that metal will not fail in shear because due to this shear, same amount of normal stress or that we have studied in last question. Okay, same amount of normal stress will be acting at 45 degree to the plane of shear. So maximum tension will occur at that state. Okay, so maximum shear stress will maximum normal stress will occur at that state. So the metal will fail at that thing. Okay, so reading out for you. Cast iron is strongest in compression and weakest in tension. So when compressive load is applied on the cast iron, maximum shear stress will occur at 45 degree to the applied compressive load, whereas tension is applied maximum when the torsion is applied, maximum tension occurs at 45 degree to the applied torque. And in the first case, there is no tension anywhere, whereas in second case, there is tension at 45 degree. So both will fail at 45 degree. First will fail at due to shear, and second will fail due to tension. Okay. Next question. Stresses at a point are shown in figure. What is the shear stress on plane AC? If tau on plane BC is 40 MPa, what is the magnitude of angle theta? If AB is principal plane, what is the maximum shear stress at that point? Okay, so this is the tau acting on plane BC, and stress at perpendicular plane is complementary shear stress, okay, and which is equal in magnitude to the to that tau. So the shear stress at the plane AC is tau, but it will be opposite distance. If it is anti-clockwise, then it is clockwise. Okay, so reading out as the plane AC perpendicular to the plane of that of BC. Okay, so the same shear stress but opposite strength will act on plane AC. Okay, so that is a clockwise shear stress 40 MPa will act at plane AC, that is because tau is 40 MPa. Okay, so diagram will be like that: 60 MPa, 100 MPa, 40 MPa, 40 MPa. Okay, next, what is the magnitude of angle theta if AB is principal? Now to find out the principal plane, we have the formula that tangent to theta is equal to 2 tau xy divided by sigma x minus sigma y. So we can put this value. This is 76, comes out at 76.71. Okay. So at this plane there is no shear stress. Okay. So this is the because this is the principal plane. So at this plane there is no shear stress. Okay. Next, next question is At a point in a material, stresses on two mutually perpendicular planes are 60 Newton per mm square tensile and 40 Newton per mm square tensile. The shear stress across these planes one sorry 1 5 Newton per mm square. Find the magnitude and direction of the resultant stresses on a plane making an angle 40 with the plane of first stress. Also find the normal and longitudinal stresses on this plane. So first stress is 60. So this is 60. Sigma x is 60. Take it sigma x. Second stress is 40. So take sigma y 40. Okay. So tau xy is 15. Tau xy is 15. Okay. Tau xy is 15. Now we have to find out the resultant stress on a plane 40 with the plane of first stress. So this is the plane of first stress. This is the plane BC is the plane of first stress is sigma and making an angle 40 with this theta is equal to 40 degrees. Okay, so either we can solve it by direct formula by putting theta is equal to 9. We have the formula for the stresses making an angle theta with AB. Okay, but here the angle is with BC. So we can put in our formulas theta is equal to 90 plus 40 130. Okay, we can solve from that or we can drive the formula. Okay, so by first principle so sigma x is 60, tau xy is, so draw this block. Okay, so sigma x tau xy is sigma y and suppose the stresses are acting as normal stress is sigma theta and shear stress is tau theta. Okay, so this is multiplied by area sigma s into BC, tau xy into BC, or tau xy into EC, or sigma y into EC, or sigma tau xy into BE, sigma theta into B. Okay, multiply with the respective area. Assume the width of the block is different. Now the equilibrium diagram is this sigma x is acting in this direction. Okay, this tau xy is in this direction. Similarly, sigma y and tau xy are acting in vertical direction, and this is acting at an angle theta. Okay, this is the angle acting at an angle theta. Okay, now rotate the diagram, make them vertical and horizontal. Make tau theta, sigma theta as vertical and horizontal. Okay, so these are this is vertical, this is horizontal. Now resolve that. So uh, first we have to find out sigma theta. Sigma theta b. This will carry the force component. This will carry the side component. Okay, now AB divided by BE. Okay, we have BC by BE as BC by BE as BC by BE as cos theta. Similarly, EC by E as sin theta. Okay, EC by E is sin theta and BC by BE cos theta. We can drive this and then put theta is equal to 40 degree. Now we have to put 40 degree. Okay, because we have drive according to that. Na? Similarly, when we resolve vertically, okay, so we can get that formula for and by putting BC by B is equal to cos theta and BC by B is equal to sin theta. So and put the value we can get tau theta. So once we have found out tau theta and sigma theta, we can get sigma or resultant stress. Okay. Next question is an element with stresses acting on it at a point is shown in figure 2. Sigma x is 80 MPa, sigma y is 100 MPa, tau xy is plus minus 50 MPa. Okay, the diagram is shown. Okay, determine the normal and shear stresses acting on a plane AB. This is the plane AB. Okay, whose normal is at an angle 110 to the respect to x axis. This is x axis, this angle is 110 Okay, Principal, second, the principal is in their direction, maximum shear stress on there, and its location. Okay, so we have this plane. Okay. This plane is making, its normal is making 130 degree, sorry, 110 degree with the x-axis. Now the plane will make 90 110 minus 90, that is 30 degree. Okay, so the plane AB will is making 30 degree with the x-axis. So we have the formula for that, sigma theta and tau theta, and we'll put in the formula theta is equal to 30 degree. Okay, and we'll find out sigma theta and tau theta. Okay, so this is sigma theta and other one is tau theta. Next, so this is sigma theta compressed in this is tau theta. Now we have the formula for principal stress is sigma 1, sigma 2 is equal to sigma x plus sigma y by 2 plus minus 1 by 2, sigma x minus sigma y square plus 4 tau square xy. Okay, put the value, you can get the principal stresses. And we have also the formula for direction, that is tangent to is equal to 2 tau xy sigma y minus sigma x. So put the values, we can get theta. Okay. Now the maximum shear stress is sigma 1 minus sigma 2 by 2. We have found out sigma 1 and sigma 2. Okay. So we can get tau max. So this will be tau max. So we have also the maximum shear. To find out the plane of maximum shear stress, add 45 degrees to the plane of principal stress. So this will be 120 and this will be 210. Thank you. Thank you. And then we will do some more questions next.